going to look at how to deal with systematic uncertainties. So just a reminder, systematic uncertainties have a non-zero mean. So this means that we are either consistently overestimating the value or underestimating it. We're going to start by considering how to deal with constant systematic uncertainties. The most common cause of constant systematic uncertainties are zero errors. So this is where the equipment that we're using isn't zeroed correctly when we start to take the measurements, and we have an additional value added to each of the measurements we take. One way to deal with these zero errors is to plot a straight line graph so that the gradient of the straight line graph is the value that we want. In this case, if we add a constant value to the x values, it will shift the graph across, and as the graph moves across, the gradient doesn't change, and so we still end up with the same gradient. If we were to add a constant value to the y values, it would shift the graph upwards, but it again wouldn't affect the gradient of the graph, and so the value that we calculated would be unaffected. Let's look at this in a bit more detail. Imagine that we wanted to measure the density of a specific liquid. We know that density is equal to the mass over the volume. So one way to measure the density is to measure the mass of a few different volumes of the liquid and then use this to calculate the density. So we get a set of scales, and we're a bit careless and don't realise that before we put anything on the scales, it is reading 5 grams. We then proceed to measure a few different volumes and we record the mass of the liquid. So the results that we obtain are written down here. Now, in order to calculate the gradient, what we can do is plot the mass along the y-axis, it's the rise, and the volume along the x-axis, it's the run. The gradient is then given by the density. Now in this case, each of our masses is 5 grams too heavy, and so this causes our line to actually be shifted up a little bit, but as you can see, it doesn't affect the density. So now we can use the gradient of our graph to calculate the density, and you can see that this is totally unaffected by that zero error. Now, if the systematic error that we're dealing with is not constant, then it can be a bit more difficult. The best way to deal with the uncertainty in this case is to eliminate the uncertainty. So this can be done by properly calibrating the equipment. One way to do this is to use things which are known to test the equipment. So for example, if we wanted to calibrate scales to measure masses, we might get a set of masses that was known very accurately, and we can then plot the known mass versus the measured mass. Then whenever we make a measurement of an unknown mass on these scales, we can just look back at this calibration curve to see what the actual mass is. So we've now looked at how we can deal with systematic uncertainties.